In this video, we are going to talk about how to determine the formulas for different types of ionic compounds. But before we get started, let's go ahead and review the three different types of compounds. We have covalent compounds, acids, and ionic compounds. And it's important to be able to tell the differences between these three types of compounds by looking at the chemical formula. So covalent compounds contain primarily nonmetals. And sometimes covalent compounds can also contain metalloids. Covalent compounds never ever contain metals though, and that's primarily how we can tell them apart from ionic compounds. They will never ever have metals in them. So looking down at this list of compounds, we can start by just looking for the covalent compounds. Looking at this first compound, Zn3p2, well, Zn is zinc, which is a metal, so that can't be a covalent compound because it has a metal in it. Then looking down at this second compound, N2O3, nitrogen and oxygen are both nonmetals. So we can say that this is probably a covalent compound, but it could also be an acid. Acids look a little bit like covalent compounds, but they always start with the same element. They always start with a hydrogen. So let's fill that into our notes real quick. Hydrogen. They always start with hydrogen. And so this should be a review from your zone 1 of sorting, but I just wanted to make sure that we understand this before moving forward. And then last but not least, ionic compounds always contain a metal and at least one nonmetal, sometimes more than one nonmetal, but they always contain that metal. And the metal will always come first in an ionic compound, a metal and a nonmetal. So make sure that you have that information in your notes and that you understand it and can use it to sort compounds into categories, much like what we can do down here. So using those three rules, this first compound, Zn3p2, because it has that element zinc in it, we know zinc is a metal, that's going to go into the ionic category. So I'll start here by writing that into the ionic category, Zn3p2. We'll put that in the ionic category, and then we can check that off. N2O3, this we said doesn't have any metals in it, and then we had to question, does it start with a hydrogen atom? And no, it does not start with a hydrogen atom, so this fits into the covalent category. So N2O3 we'll put in the covalent category. The next compound, H2SO4, we have hydrogen and sulfur and oxygen, and none of those are metals. So we need to check to see if it starts with hydrogen. And indeed it does, this time H2SO4. So it does start with hydrogen. So instead of putting H2SO4 in the covalent category, this will fit into the acids category, H2SO4. So that is our first acid. This next compound, KCl.H2O, potassium, this first element, is a metal. So this goes in the ionic category. Even though it has this weird .H2O part, this is a special kind of ionic compound. It's called a hydrate, but you don't really have to know that. You just need to be able to tell that because it has that metal, potassium, in it, it is going to go into the ionic category. So I'll put KCl.H2O into that ionic category. And then our last compound is SCl6. Sulfur and chlorine are both nonmetals, and it does not start with a hydrogen, so this will also go in the covalent category, SCl6. So hopefully that was a good review from what you did yesterday. let's move on to the new portion of today. The crisscross method is a quick and easy way to determine the chemical formula for an ionic compound. And as we know, in an ionic compound, the metal will always have a positive charge. And so right here in our blank, we'll fill in that the metal will always have a positive charge. Positive. Please make sure that you have this information written in your notes for later. And the nonmetal, as we've discussed before, nonmetals are anions, and so they always have a negative charge. So we have the positive metal and the negative nonmetal. And in an ionic compound, the net charge, meaning the overall charge of the compound, has to be 0. And I'm going to show you what that means by drawing some pictures. So to draw a picture of sodium chloride, we need to know the charge of both sodium and chlorine. So if we take a look at our periodic table and find sodium, it is in group 1 of the periodic table. So sodium, each sodium atom is going to have a positive 1 charge. So I'm going to draw sodium with a positive 1 charge. I'll show my atoms as circles. There's my sodium atom. But I need to balance that +1 charge with an equal amount of negative charge. And so my other atom that sodium's bonding with is chlorine. And remember, for negative ions, we change the ending to "ide." So chlorine we call chloride when it's in its ion form. And if we take a look at our periodic table, chloride or chlorine is in the -1 column. So its ion is going to have a -1 charge. So to balance out the charge, I just need one of each of my ions. +1 balances out the -1. And our overall charge, we have a net charge of 0 overall with that +1 and -1. So some compounds are really easy to balance out the charge to 0, but other ones are a little bit more complicated, like sodium nitride. So once again, we have sodium, which has a +1 charge. But if we look up the nitride ion, or the ion formed by nitrogen from the periodic table, nitrogen has a -3 charge. So let me draw my nitrogen atom here with its -3 charge. And I didn't quite do that in the right place. I'll do that again. Nitrogen with a -3 charge. So if we have one nitrogen and only one sodium to balance it out, our overall charge is going to be -2. And that's not possible. Nature won't keep that overall charge of -2. It wants to get to 0. So what nitrogen has to do is it has to find not just one sodium to bond with, but it has to find 3 sodiums to bond with. So that way those 3 sodiums together can balance out that -3 charge on our nitrogen atom. So the 3 sodiums together have a total of +3 charge to balance out the -3 charge of the one nitrogen, giving us an overall charge of 0 once again in the end. So drawing a picture each time you want to figure out a formula isn't probably super convenient, so there's a much easier way to do it, and it's called the crisscross method. So the crisscross method is just an easy way to figure out how many of each atom are needed to have an overall net charge of 0. And you can do the crisscross method in 3 easy steps. The first step is to write out the 2 ion symbols. So we'll take example 1 here. The 2 ion symbols for magnesium sulfide would be the ion magnesium and the ion sulfur. So we will start by writing out those 2 symbols. Magnesium, if we take a look at our periodic table, it's in the +2 column. So magnesium's ion symbol is Mg with the +2 at the top as the superscript. And then sulfur, sulfur. Sulfide is in the -2 column. So sulfur's ion symbol is S with a -2 as the superscript. So there's step 1. Then the next step of the crisscross method is that the charge without the symbol or the sign becomes the subscript of the opposite element. So what I mean by that is we'll write the formula, we'll write Mg, and take the 2 from sulfur and make it the subscript on magnesium. So the 2 now comes to the bottom as the subscript, and that tells us how many magnesiums we need. And then we'll do the same thing. We'll take the superscript, or the charge from magnesium, and bring it down to become the subscript on sulfur. Easy enough. Step 3 is just to reduce if you need to, and then we don't show a subscript of 1 in chemistry. So the 2 and 2 here can be reduced. 2 and 2, we can divide both of those by 2 and simplify down to Mg1S1. But because we don't show a 1 in chemistry, our final answer we'll write without those subscripts of 1. We'll just write it as Mgs. So here's our final answer, our final formula for magnesium sulfide. And if we were to draw a picture of this, magnesium has a +2 charge and sulfur has a -2 charge, so we only need 1 of each to create a balanced formula with a net charge of 0. So we do know that this indeed is the correct formula. And instead of having to draw a picture, all we had to do was crisscross the charges to make them the subscripts. Let's try one more example here. Aluminum chloride. So aluminum, if we take a look at our periodic table, aluminum is right here, atomic number 13, and it has a charge of +3. So we'll write Al with a superscript of +3, and then chloride, Cl, is in group 17 and has a -1 charge. So we'll write Cl -1. Then our next step is to cross the charges over. Make the charges the subscripts. So Al, we'll take just the 1, not the sign, but just the 1 from the chlorine. And then Cl, we'll take just the 3, not the plus sign, but just the 3 from the aluminum. Then we can't reduce here, but we can get rid of the 1 for aluminum because a 1 is implied in chemistry. So our final formula here will be Al, Cl with the subscript of 3. 1 aluminum and 3 chlorines. So as we've talked about before, if you have a transition metal, you can't know the charge of that transition metal by looking at the periodic table. So instead, scientists came up with a way to identify what charge the transition metal has in its chemical name. And that is to write a Roman numeral. The charge is given as a Roman numeral. I'm off the screen here, I'll rewrite that. Roman numeral. Since metals are always positive, we know that the sign on our charge is going to be a plus sign, but we just need to know how much positive charge the transition metal has. And then once we know that charge of the transition metal, we can find the charge of the nonmetal on the periodic table. Now, to be able to write formulas for ionic compounds that include transition metals, you do need to know Roman numerals 1 through 10. So if you're not familiar with Roman numerals are made up of letters. They're the letters I, V, and X. And there are various combinations of those letters I, V, and X. And you should memorize Roman numerals 1 through 10 to be able to write formulas really quickly and be able to do it without looking up that Roman numeral. So let's do a few examples here. So our first example is vanadium chloride, but we don't know the charge of vanadium from looking at the periodic table because vanadium's in the transition metal section. Remember, the transition metals are these elements in the D block of the periodic table. Since we don't know that charge from looking at the periodic table, it's conveniently given to us in the chemical name. This Roman numeral II is Roman numeral 2, and that's telling us that vanadium, our ion symbol for vanadium, has a charge of positive 2. So this 2 is telling us the charge of the vanadium. Then we can get the charge of the chlorine by looking at the periodic table. And if we find chlorine, it's in group 17, so it has a negative 1 charge. So V plus 2, Cl minus 1. Now we'll just crisscross the charges. So the 1 becomes the subscript on vanadium, and the 2 becomes the subscript on chlorine. And then in our third step, we don't need to reduce here, but we do need to get rid of our 1. So instead of V1Cl2, our final answer will just read VCl2. We have one more example here. Our next example is iron oxide. And when we read these, we read them with the charges, but I'm going through slowly just to show you how to figure out what the charge is. So this first, in example 3, we would have read this off vanadium 2 chloride. And in example 4, this is a Roman numeral telling us the charge of the iron. So this is Roman numeral 4, so we would read this iron 4 oxide. It's telling us that the iron, chemical symbol Fe, has a positive 4 charge. Then oxygen, we'll need to look at the periodic table to figure out its charge. It's right here, and so it has a charge of negative 2. So iron 4 oxide. If we crisscross those charges, we get Fe, and just the 2 comes down, and O, just the 4 comes down. So we never carry down the sign, we only carry down the number that comes from the charge. This time we have to simplify or reduce, and we will have to then remove the 1s. So 2 and 4 are both divisible by 2. So we can simplify our formula by dividing by 2, and that gives us Fe1, O2. But we know that we don't show a 1 in chemistry because it's implied, so we'll simplify our final answer to just read FeO2. So that's pretty much all there is to it, but I do want to take a second just to do a few mixed examples here. So you have to be able to look at the formula and then determine if you have a transition metal, that you have a Roman numeral 4, or you have a main group metal. So in this first example, calcium arsenide, calcium is a main group metal. Calcium is right here on the periodic table. It's in group 2, so it'll have a positive 2 charge. So to start out, I'll write my ion symbols, Ca plus 2. And then arsenide is going to be arsenic. And if you find it under the periodic table, it's number 33. Its chemical symbol is As, and it has a charge of negative 3. So we'll put its symbol As minus 3 as the superscript. We'll go ahead and crisscross those charges. So we'll get Ca3, As2, and then we don't actually need to simplify here at all. So I'm just going to rewrite my final answer and box it in. Ca3, As2. Make sure when you go through practice and you take a quiz or a test, you're showing both ion symbols, you're showing your crisscross, and you're boxing in your final simplified formula. You will get points for both ion symbols and for your correct simplified final formula. So make sure you're showing each step carefully. This next example is zirconium, and it has a Roman numeral 6 sulfide. So I'm going to go ahead and assume that zirconium is a transition metal. If you want to be sure, just double check that it's in your transition metal section. Zirconium is indeed a transition metal. It's element number 40, and its chemical symbol is Zr. So we'll start by writing that chemical symbol, Zr, and then the charge of zirconium says Vi, which I know is Roman numeral 6. So I know zirconium is going to have a positive 6 charge. Then sulfide, sulfur's chemical symbol is S, and then if we look at our periodic table, sulfur is in the -2 column. So our ion symbol is S with a -2 charge. Then to get our formula, we'll do the crisscross. Zirconium is going to get the 2 from the sulfur, not that negative sign, but just the 2. And then sulfur is going to take the 6 from the charge of zirconium. 2 and 6 are both divisible by 2, so I'm going to divide by 2 here to simplify my formula. We'll get Zr, we'll write that under here since I have room, Zr1, S3, 6 divided by 2 gives us 3. And then our final answer, we need to get rid of that 1 and write the simplest version of our formula, Zr S3. Our final example is sodium telluride. So sodium has a weird chemical symbol. Sodium is Na, and hopefully you're starting to get used to the chemical symbols. Na, our sodium is in the +1 column, so the ion symbol for sodium is Na with the +1. And then tellurium, or telluride, is over here in the -2 column. So we'll put Te with a -2 charge. Then when we crisscross, or sometimes we like to call it cross and drop, Na will take the 2 from the tellurium, and tellurium will take the 1 from the sodium. But then we do not show a 1 in our final answer, so I'll just rewrite Na2Te as our final answer here. And that's pretty much all there is to it. If you want to see more examples, there is a video to go with 2B, so I'd encourage you to watch that. But otherwise, use these examples that we've done as a model to do other problems. And with some practice, you'll be really good at this in no time.